Okay, we wait another 5 minutes for all of you, for all of your friends to come in. Okay, still less than 50% now, even though the attendance show, I mean, 100. So, wait another 5 minutes and then we will start our lecture number five. Hello? Yes, Allah Wabarakatuh, and good morning to everyone. How are you guys? Is it okay?
Okay.
Yes, sir.
Doing
Uh, yeah. I'm not sure whether that. I think there are survey whether whether the students prefer the physical class or online class. Not sure whether you already have received that or not. Have you guys received any of that to answer the survey?
Is it in Spectrum or
No, 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 no. I think it's not in the spectrum. Forgot already. So, is it you guys prefer the physical or the online class?
Sir, is it possible if you can share the survey in the chat here?
Yeah, sure, sure. I will try to find it, but I try to find it. Okay. Yeah. So far, yes. Everything. My lecture is recorded. Just that. I may have to apologize if I haven't had a time to break it down into smaller subtopics, or I know for you guys to like listen to lecture for more than 1 hour or almost 2 hours lecture video is it's really you have to be patient and stuff. But I try my best later because as I mentioned before, video rendering takes so much time. I try to be after this I will try to break it up into smaller topics. If not all, maybe some of your lab topics or something. Okay. So this lecture also gonna be recorded. How many of you now? 159. The registered, I think 300 something. That's okay. Okay, I'm gonna turn off my video to conserve some bandwidth. Just bear with me a second. Anyone, can you see my slides?
yes?
Yes,
yes.
sir.
Wait. Wait. Okay. Okay, so today our lecture title will be a process management. So you have learned before memory, conventional one, a virtual memory, and then you also have learned about processor management. So now to the next topic, lecture number 5, process management, job management, basically. Wait, forgot that. Forgot my the tablet. Wait. Okay, there's some analogy for the process management. Okay, take an example, the staircase. Wait, where is it? For some reason it doesn't. Never mind. Okay, the staircase at the building was built as a fire escape route, but people in the building often take the stairs instead of the slow lift. So it depends whether some of the lift, lift or elevator in the building is very slow, or some is very small. So people tends to go to the stairs. Okay, every building must have stairs. Every building, like in Malaysia, you have like if more than 4 levels, it is compulsory to have a lift, and of course stairs for like fire emergency. So the stairs is only wide enough for one person. Okay, the stairs only wide enough for one person. So imagine this a very small stairs that at one time only one person that can go, or can pass through that stairs. Let's say in normal circumstances, traffic flows is very smooth. Okay, you can go both. I mean, if one person goes, imagine this only one way, depending on the which ways you want to go, either going up or going down. So traffic flows smoothly unless there are two people moving in the opposite directions. So there's a landing between each floor that is wide enough for people to share. Okay, a problem occurs. So you have like a stairs here, and then you have wait, just make a little bit more. So this stairs like really only one person. So, but at the same time, at the each level landing, we call it a landing level, is enough for two persons to like land or stand at one time. But the stair itself is a very small stairs. Only one person, where either he can go up or he can go down, or he can goes up. All right. A problem occurs when someone going up the stairs meets someone coming down and each refuse to retreat. So you have here this person wants to going out, wants to going down, and this persons want to go up. So you have here this deadlock. No one wants to give up, or no one want to retreat to the landing position, either on the upper side or on the lower side. So this situation we call it a dreadlock. Of course you have been in a deadlock situation a couple of times. Okay, so another possibility, a few patients People wait on the landing for a break in the opposing traffic and the break never comes. So let's say you are in the opposing traffic. We have example diagram for that. And if like nothing happens, no one can go out, or no one can go out. Everyone stops unless there is an outside intervention. This condition will never gonna be solved. So this is what we call a starvation. This is what we call a starvation. So this intro. There is a visualization of the deadlock. So a deadlock in systematic meanings means a situation where the resources needed by a job to finish execution are held by another job. Okay, they just like the example of the stairs. Both of the persons, or need to do some things. One person maybe have to go to other departments that are located down at the lower level floor, and that another person have to go to the department that on the upper level floor. So the resources is the stairs. So needed by job to finish again are held by another job. So this is a deadlock situation. The resources are needed by both men, but at one time only one person can go up or go down, goes up or goes down using the stairs, which in turn is waiting for other resources to become available. No one wants to give up. I don't want to give up. I will just wait here. If I just wait here until at the end of the time, okay? I don't want to give up my position here. So also it is also sometimes termed as a deadly embrace. Okay, deadly embrace. So these are deadlock situations. Okay, the sticky situations. And then you have a starvation, the results of conservative allocation of resources in which job is prevented from executing because it keeps kept waiting for resources that never become available. So this like the keyword, the conservative allocation of resources in which a job is prevented from executing because it is kept waiting for resources that never become available. So you're waiting in the traffic jam, but it's like really bad traffic jam. No one can move. So this is a diagram of. We don't have a diagram yet. So imagine it's a traffic jam, which I think slide number 6 or something. So a deadlock affects more than one job. Okay. Imagine that person that going up or going down using the staircase. Okay. It affects more than one job. That person is a job. Example of deadlock, traffic jam. Only outside intervention can resolve a deadlock. Okay. If there is no outside intervention, it's gonna be there forever, starvation. Unless of course in OS you can just forcibly shut down the PC or control alternate delete or something, okay? And you end tasks and the jobs, whatever job you just feel annoying or taking too much processors load. Deadlocks are prevalent in interactive systems like the modern time because the system is more flexible than a batch environment. Batch environment where, just to recall, where the job is coming in batch, in a groups. You settle that batch first, and then another batch coming in. The interactive system is a more dynamic. It's based on demand. Okay, it doesn't like save or allocate any memory, allocate any resources. If allocate any idle resources, this is what we call interactive systems. And interactive system improve the use of resources through dynamic sharing, but this also increase the possibility of deadlocks. Okay, this is where the traffic jam, a deadlock in the traffic jam. Okay, where this, let's say this and this one as well cannot move on this side, So okay, on this side. So any of the direction, the car cannot move because this is a deadlock. Okay, unless like some intervention or something, meaning that the police traffic only allow a certain route to be, to clear first, or maybe some accidents happens if still waiting for the police or the ambulance to take the or tow truck to take the uh, affected vehicles or to take the patients. We are stuck in the deadlock situation here. So no one can move forward until someone moves out of the way. No one can move out of the way. Okay, you cannot continue because someone have to move forward, move out of the way. But there are no one that can move out of the way until someone advance or rear line moves back. So only as I mentioned, only outside intervention can solve these issues. So usually occurs when the non-shareable preemptible resources, files, printer, so in the OS, in the computer systems, are allocated to jobs that eventually require other non have been locked by other jobs. You have to wait. Files, printers and everything have to wait until that job's to be done. So you have here 6 cases of deadlocks. First, the deadlocks on the file request. And then deadlocks in the database management, dedicated device allocation, deadlocks in multiple device allocation, deadlocks in spooling, or deadlocks in hard disk sharing. So first we go into the deadlock on file request. It happens when jobs are allowed to request and hold files for the duration of the executions. Wait, sorry. Okay. So jobs are allowed to request and hold files for the duration of the execution. Example, a home construction company has 2 departments, a purchasing P1 and sales P2. Both departments need access to 2 files, which is inventory F1 and the suppliers F2. For some reason I cannot use my tab. Never mind. Okay, a home construction company has 2 departments, purchasing P1 and sales P2. Okay, and then they have to access 2 files, the PC, inventory F1 and suppliers F2 to update the daily transaction. So a deadlock occurs when the following sequences of events takes place. Purchasing P1 accesses the supplier file. Accesses the supplier file F2 to place an order for more lumber. Just bear with me for a while. For some reason, can I use my writing tab? Okay, sorry for that. Okay, deadlock occurs when the following sequence of events takes place. So purchasing P1 access the supplier file. So you have like a file. You have a purchasing P1 here, and then access the supplier file F2. Sales P2 access the inventory file F1. So sales P2 F1. So first they try to request, the P1 request, and it is F2 allocated space for P1. This one is allocated. And then you have a sales P2 access the inventory file here. Try to access the inventory file, it requests. And F1 allocated the resources to P2. P1 doesn't really, sales P2 access with them to reserve parts that will be required to build the house ordered that day. So at the moment, P1 doesn't release F2 because P1 is using F2. But at the same time, he needs P1 has to access the inventory file for some other matters. So he tried to request the F1 request. F1 to verify the quantity on hand before placing an order, but P1 is blocked. So when F1 heard the request from P1, but it cannot allocate the resource, to FP1 because at the moment is serving P2, process 2 or jobs number 2. So this is the jobs, this resources. F1 is the resources. So it blocked here. And P2 doesn't release F1. P2 doesn't but request for F2. At the same time, P2 also want to request F2. Okay, he wants to check something. But F2 at the moment allocates its resources to F2. So this one will be blocked. P2 doesn't release F1 but request for F2 to check. So this is a deadlock situations. So this you have here request. Okay, this is the first one. Purchasing P1 need to need to request suppliers F2 and it is allocated. So number 3, inventory F1 requested the sales P2 and it is sales inventory will be allocated to F1. Sorry, this is the really wrong one. So this is allocated. And then at the same time, number 5, P1 tried to access the inventory. Okay, try to access the inventory F1. But the request is blocked because at the moment F1 is serving P2. And P2 tried to access the supplier F2, try to request, but it's blocked here. Both here block. Because at the moment supplier F2 is serving purchasing P1. Okay. So you get I hope that you get the idea of the deadlock on the file request. Then we have a deadlock in the database. We have a deadlock in the database. So occur if two processes access and log records in database. Okay, you have a two database. Somehow you have a database. You have a multiple database files. Like this is database for the list of customer, and this is database for the list of suppliers. List of a multiple databases file. So one of the way to to manage the deadlock in database is by locking. Is by using locking. Locking is a technique used to guarantee data integrity by locking out other users while working with the database. So data integrity, meaning that locking is used to protect or to guarantee the data integrity, meaning that any files or data is not modified. Okay, it's not modified or being altered. So this is what we call integrity. The files is as it is, not modified or not altered. Data integrity. So you lock that part of the file. So you lock, okay, while you serving other users, you lock other users to access that database file, okay? Let's say this user one is DB1, database one. Is now DB1 is allocated to user one, but user two, user three, user four try to access DB database one, but they are all blocked because it is now allocated, locking. User one already locked database one for him to access the resources and the resources to serve him. Locking can be done at 3 levels. Lock the entire DB for duration of the request, okay, until user one finish everything. It will release back, unlock, lock a subsection of the DB. Maybe DB you have a couple of, okay, a name, metric numbers, name, metric numbers, name, metric numbers, grade. What else you have? I mean, you have a different column. So you lock one column, you only lock one column, while the other two columns anyone can access that. But the column that has been locked, no one can alter that, maybe view or something. Or lock individual record, just a number of individual. Let's say John here, you have John Smith, Ali, Ah Chong, and you only lock John. This like John here, John, you only lock that part, the individual file, lock the individual record. So locking increases the possibility of deadlocks. So because you lock, so anyone, only that part, it's like a toilet, okay? It's like a toilet that only have one. If you go in number 2, only have one. So it's a deadlock situation. No one can use that toilet unless that current user finish, of course. And of course, if you not, flush, if it does not flush or whatsoever, or the stuck, everything, pipe stuck or something, or no waters, you still cannot use. So this, imagine like a toilet that have only one toilet bowl, all right? Before you going number 2. So another example is a system logs a record when it's accessed until the process is complete. Two processes P1 and P2 need to update 2 records, R1 and R2. So the following sequence lead to a deadlock. P1 access R1. So this one P1 and this one is R1. P1 what? 2 processes and 2 records. So P1 and R1. So P1 request and allocated. Request and allocated. And then you have a P2 here. And you have here R2. You want to access the record, so you request, and this one you allocated. Sorry, request should be a dot line. Just bear with my handwriting. Okay, request, and this one is allocated. P1 request R2. So now P1 wants to request R2. I am greedy. I need R2 as well. Sorry, this is supposed to be a. It's supposed to be a when I just want to try to separate between the request and allocated. So request R2 request. But P2 already locked record 2. No one can use R2 except for me. So it is blocked here. And at the same time, P2 try to request R1. Try to request R1 request. But it's also blocked because R1 is serving or being allocated to P1. So if you do too many locking, too conventional, okay? You don't want someone else to access it except you. While while you entering this or while you're doing that, no one can disturb you. So you will increase the deadlock situation. People might hate you, okay? So alternatively, do not use locks, but this may lead to integrity problem, okay? Data can be easily modified in a wrong way or data can be altered, okay? Many bad guys love this. The updated record also might include only some of the data, okay? Some of the effect of you don't do the locking, some of the updated records might not include a sum of the data. It's not correct. So this is known as a race condition. Let me show you. Like, okay, you have let's say you have a one process that you have a one process here. Read x, okay, and then write x equal to x. So W is write, this one read x, and W you write x equal to x plus 10. So the program read x first, so x a shared date, x is a 10. So read x and put x equal to 10. And then write x plus 10, so x is equal to 10 plus 10 is 20. So the final value being recorded is 20. But let's say you have a let's say you have a two process. This one read x. Okay, x a shared variable. Okay, x a shared variable. X is a shared variable. So read x and write write x equal to x plus 10. And of course you have this is a process 1 and you have a process 2. Also read x and write x equal to x plus 10 as well. You have that. You have two process. Okay, the first process, let's say, come at not at the same time, but almost at the same time. So first you have process 1, read x. So it's recorded x is equal to 10. This one first, okay. This one number 1, and then suddenly P2. Also, this process that this is the like thread process that been chopped into smaller threads. So number 2, process 2 read x. So process 2 also we record x is equal to 10. Let's say come back to this one, thread number 2. So this is number 3. So x will write, the process will write x is equal to x plus 10. So process 1 will record here x is equal to 20, 10 plus 10. But this is a process. This is thread number 4 comes in. So process number 2, thread number 4 still read x equal to 10. And when it wants to write x plus 10, it will write x 10 plus 10 also 20, which is wrong because it's supposed to be 20. This, in order for you to prevent this, you must lock, meaning that you done the P1 first. So when you done a P1, x will become 20. And when the process number 2 try to read what's the current value of x, it will read 20. And 20 plus 10 is 30. So this is what locking try to prevent. A race condition where you suffer data integrity. Data has been modified or altered in a incorrect way, in a wrong way. But of course, if you lock too much, your system will be too slow, and it's not dynamic. Okay, this is a parallel programming problem. So we will not go. But I'm showing you the race condition, the simple one, the read and write x. So this is examples from the slides. So Chow, you have a GP of 2.5. And currently he stays in College 12 or 12 residential college. Okay, 12 Residential College? Any one of you stay in the 12 Residential College?
No.
I think science computer mostly 8 and 10. I think so, but 12 Residential College. I have become a fellow there before. It's the biggest college at the moment in UM. And because it's the biggest, newest, it has a very, nice floor in here. It has a very nice room, and it has its own lake or some lakes, even outdoor gym. Okay, I have been a college 12 before, a fellow. Now I'm fellow of second college. So you have Chow GPA 2.5 and Address College 12. All right. Okay, process one only grade process, reads data. Okay, reads data, grade process and reads data. Grade process meaning that write a new value to the process. Reads data, reads grade process. Sorry, this is a grade. Only modify grade. Okay, grade GPA. And it reads data. Only reads data, doesn't do anything to data. And process 2 only address process. Address. The address part. And only reads the reads the data. Sorry, reads the data as well. So Chow actually got a GPA 3.0 in the new semester. I mean, in the current in the previous semester, the semester that just recently finished. Okay. But GPA updated, grade process. College to section 17. Okay, section 17 PJ. Maybe Chow is not really active, so he has been kicked out from the college. Okay, if you want to stay in the college, you have to be active in the student activities. And of course you have to attend the programs that managed by the colleges. So if you don't attend that, you got demerit and stuff. So Chow don't have enough marks to stay in the college, so he has to move out. So this one, Chow only address is updated but not the GPA. So the first process one rewrites record to the database file with the new GPA, but it reads GPA 3.0 and address college 12. It does not update the new location where Chow transferred to. But and then P2 update the database file. P2 rewrites record to DB. Rewrites. Rewrites record to DB. It only update address, but not the GPA. Okay. The system said, okay, Chow, you are not attending last semester, so your GPA is 2.5, or you failed the whole subject, your GPA is still 2.5, something like that. But we have a record of you moving out. So this is wrong way. This is what we call a race condition. Process 1 and process 2 try to what we call that, try to compete with each other to update the record. So this one. So it also can be a reverse situation where P2 comes first and then P1 rewrites, but still it will return the same problem. If like P1 rewrites, P1 only have this one. GPA is correct, but address is 12 college, which is wrong. Still a race condition problem. Okay, now we go to the deadlocks I think this is number 3, yes. Deadlock in dedicated device allocation. 2 users run 2 programs, P1 and P2. And both programs need 2 tape drives to copy file from one tape to another. It's mainly your hard drive. Maybe want to you from your thumb drive to your SSD or something else. So the following sequence leads to the deadlocks. P1 request tape drive 1 and gets it. So P1 tape 1. P1 request and allocated. P2 request tape drive 2 and gets it. So P2 tape 2. Request allocated. By the way, this visualization of a direct a visualization of okay, there is one in mathematics. There is one field that is called graph theory. Graph theory. Okay, this one represent nodes. Okay, this whatever this represent P1, T1, P2, P2 represent nodes, and this one is a direction. It can be both way, like it can be bidirectional or one directional. Bidirectional or directional. Bidirectional means two ways. Directional only one way. Okay, this is what we call a graph theory. Just for you to visualize. We use a lot of graph theory in the science computer. Okay, we use a lot of graph theory in science computer, regardless what courses you are. Not even not just science computer, used in medical, engineering, and others. Okay, now we go back. P1 request tape 2 drive, but it's blocked. Same. P1 tries to request maybe some files are allocated in T2 request, but it's blocked. It is blocked here. And P2 try to request T1, but it's also blocked because of course T1 is allocated or serving P1 and T2 is allocated and serving P2. Neither job can continue because each is waiting for other to finish. No one wants to back down. Okay, you have to force it to stop the operation. You have to force one of the process to stop the operation, terminate. Or if you just if like become the situation become too difficult to control, just restart the PC. Okay, that is the simplest troubleshooting that you can do. Of course, it's easy, but you don't. It's not really effective, but it works. Believe me, it works every time you try. If you don't have any ideas, just plain lazy to to investigate what's the problem, just restart. This is a basic troubleshooting for all electronics problems. So deadlocks occurs when several processes in multiple device allocation. Occurs when several processes request and hold on to dedicated devices while other processes act similarly. Okay. So there you have a several process request and hold on to dedicated devices. None of the jobs can continue because each is waiting for resource help binary. Just similar with others deadlocks, deadlock situation. So you have here, okay, P1 try to tape drive allocated, and then where's okay? This one is number 1, number 2. Printer request P2 request a printer and is allocated. Now P2 is using the printer. Okay, good. 5 is what? P3 try to request the plotter. The plotter, I'm not sure. I mean, never mind. A plotter and try to allocate. I mean, request and successfully allocated to P3. 5 and 6. Okay, so far so good. I mean, in order, the request, tape drive, printer, and plotter is okay. But now, where's number 7? Now P1 already accessed the tape drive. Okay, I need to print this. So request to the printer. But at the moment, P2 have his final year report of his thesis. Very thick thesis wants to submit at last minute. So now I'm using the printer. No one can use it. It's a shared printer. So P1 has P1 requested, so it is blocked here. So this one is not okay. Where is number 8? Oh, 8. So now P2, oh, I need something. I need to, okay, before I can print to the next page, I need to use plotter. I'm not sure why he need to use plotter. He tried to request the plotter by this block. Okay, block. So this one is not okay. So P2 cannot continue print because at the maybe some of the pages he needs plotter. I'm not sure what he needs plotter for, but he has to hold for a while or wait a printer to finish. But same time, P1 want to use printer. He has to wait P2 to finish using printer. So it's block 8, where's 9. So at the moment P3, I think this is on this file is on the tape drive. So request the tape drive, but it's block request. It is blocked because tape drive is allocated to P1. So you have all this sticky situation. No one can finish their jobs because it's blocked. Okay, no one wants to back down. Of course, you can shut down PC2, everything. You have to start over, and P1 can access the printer and stuff. All right, only you shut down one. Control alternate delete and task, something like that. But it's not effective way. Again, this very lazy plain way. And then you have a deadlock in spooling. Although a printer is a dedicated device, it can be transferred. Dedicated mean when you do, okay, you send you control P, you want to print something from the slide, so it is a dedicated device at that time, dedicated to serve you. It can be transformed into a shareable device by installing a disk between it and CPU. Of course, you can. I mean, in Windows, in Linux, you can just can configure it to be shared devices. The disk accepts output from several users. Okay, several users, and act as a temporary storage area for all output. Act as a temporary storage area for all output. The disk, if all users, you have user 1, user 2, user 3. Try to do, doing some assignments last minute. Typical student, last minute, they need to submit. So everyone rushing to print something to submit to the lecturer. So until the printer is ready to accept it, this is known as a spooling. Okay. Temporary storage. Until the printer is ready to accept, this is known as spooling. Your manager, your task manager. If the printer needs all of jobs output before it begins printing, but the spooling system fails the available disk with only partial complete output, a deadlock occurs. Okay. So in order for you to print, let's say this assignment needs you to print 10 pages. So it receive like 1 pages first, 2 pages, 3 pages. At the same time, user 2, okay. User 1, this is a shared printer. Okay, user 1. What happens here? Right. Okay, this one is a user 1, user 2, and user 3. Okay, user 1 send, but pages by pages. You have, okay, user 1 maybe 10 page, 10 page, and 10 page. User 1 send, but maybe the printers only receive like page 1 until page 4. U2 maybe page 1 until page 8, and U3 maybe page 1 until page 7. Your printer needs all your output before it begins printing, but the spooling system fills the available disk space with only partially completed output. The deadlock occurs. Okay, user 1 cannot print because only 4 pages submit to the shared printers. User 2 also only until page 8, and user 3 until page 7. So this is the deadlock situations. Okay, everyone rushing, want to use only one printer. Okay, the deadline for assignment completion is like 1 hour from now, but no one can print to submit. Of course, you can submit online. This is just an example. So, okay, 1 hour before important project deadline, members of your teams are frantically finishing the details. So, a last minute submission. A few minutes before deadline, all team members issue the print command. Everything all comes together simultaneously. The spooler receives the pages one at a time, but the pages are received separately. Page 1, page 2, and so on. So the printer is ready to print the first completed document. In order for the printer to print, it must be a complete document. If 10 pages, 10 pages. No compromise. Okay? No compromise. I need 10 pages. If not, you cannot continue this job. But as the spooler canvasses its file, it has the first page for several documents, but none of the complete document. As I said before, user 1 maybe have 4 pages, user 2 only have 1 to 8 pages, and user 3 1 to 7 pages. Since the printer only accepts completed files, the keyword here, completed files, none of the documents can be printed, and you cannot submit your assignments, right? So this deadlocks in spooling. Deadlocks in this sharing, okay, all of the deadlocks have a same, have a same, what you call it, same process, same SOP, we call it SOP, famous word now, everything SOP. So these are designed to be shared. These are designed to be shared, not uncommon for two processes to access different areas of a disk. So you have like a solid state device, you have a sector. I think you will learn this in a computer architecture where it is allocated into the several sector of the disk. Sector, several locations. Sector is a location in your disk drive. This ability to share creates an active type of deadlock term, live lock. Yes. Who's that? Okay, guys, finish. All right. Process use a form of busy waiting that is different from natural wait. It's waiting to share resources but never gains control of it. Okay. So if you are able to share creates an active type of deadlock terms live lock. It's just similar with the locking. Processes use a form of busy waiting that is different from natural wait. It is waiting to share resource but never gains control of it. Okay. We have here. So you have a customer service here, P1. P1 wishes to show a payment, okay? Wishes to show a payment, so issues a command to read the balance, which is stored on track 20. Track 20, a sector on track 20. Okay. Sector in 20. Okay. So depend here. Okay. Sector in track 20. While the disk control unit is moving the arm to cylinder to 20, P2 is put on hold on the input-output channel, okay? Sorry, P1 is put on hold on the input-output channel. Put on hold on the input-output channel to free the process of the next input-output request. Okay, P1 is... And P2 gains control of the input-output channel. So now P2 gains control of the input-output channel. And issues the command to write another record that's stored in cylinder 3110. So we have a cylinder 3110. So P1 now is a P2. Want to access the location of 310, sorry. And then if the command is not logged out, P2 will be put on hold while the control unit moves to the arm cylinder 3110. So because like P2 is on hold, the channel is free to be captured again by P1, which confirms its command to read from cylinder 20. So since the last command from P2 had forced the arm machines to cylinder 310, the disk control unit is beginning to reposition the arm to cylinder 20 to satisfy P1. The input-output request channel will be released because P1 is once again put on hold. Alright, P1 is again put on hold. So it could be captured by P2, which is a write command only to discover that the arm mechanism need to be repositioned. As a result, arm is constantly moved back and down. So it's like a deadlock. It's like a deadlock situations. The arms move 23, 310. Move here, and then keep on hold, then move here back. 20, 110. So it goes into the loop. All right, this is the condition for deadlock in this sharing. So all 6 deadlocks involve the interaction of several processes and resources. Each deadlock is preceded by the simultaneous occurrence of 4 conditions that the OS could recognize. Okay, it's preceded by the simultaneous occurrence of 4 conditions that the OS could recognize. First is mutual exclusion, meaning that you allocate a critical section. Okay, critical section, meaning that let's say you have a long list of the commands, long list in your coding, long list of coding, but there are some critical section, meaning that if the jobs are currently on this section, it must be completed first before you can move out to other section, other command. So this is mutual exclusion. Resource holding. So you want to avoid avoidance of deadlock, you must release the resource holding. You hold the resource. Only me can use these resources. Only I can use these resources, no one else. No preemption, meaning that you don't allocate, allocate specifically for these jobs. And you have a circular way or in a round robin fashion. I think you guys want to have a break? Or you want to continue? 5-minute breaks? Is it okay?
A break is good.
Right, okay. So we have a 5-minute break, so you can go to the toilet or drink coffee or something. All right.
Okay.
5-minute break.
Okay.
You're welcome. Okay, we will continue our class. So each deadlock avoidance, you can use one of these mutual exclusion or resource holding. You release no preemption or in a circular way. So this, how do you modeling a deadlocks? So the four conditions can be modeled using a directed graph. This is the graph, this directed graph, meaning that process are represented by circles. This is a process. And resources are represented by squares. Resources. So P1 is if you this is a directed graph, meaning that it's a you have a direction. The line have a direction, is a directional one way. So R1 is serving a P1. Resources now at current resources is held by P1. So P1 is holding R1. No one cannot use R1 except for P1. So P1 is waiting for R1. This one is a B. P1 is waiting for R1. A cycle in the graph means that there is a deadlock. If there's a cycle or loop, some call it cycle, some call it loop. Loop meaning that you are like stuck in the loop. Waiting, you request waiting, request waiting, request waiting. So you stuck in the loop. This is a deadlock. So R1 printer, R2 RT plotter, okay? P1, P2, P3 resources. So as a P1 request, I look at the printer R1. P1 release R1. So this is scenario 1, okay? P1 request and allocate the printer P1. And this one is R1. Sorry, P1 is supposed to be process supposed to be circle P1. It doesn't matter, but this textbook use circle. So R1 is the resources. For P1 request R1 and it is allocated. And then to P1 release. So finish. So it's free now. P1 and R1 free. P2 request. So you have P2 here, and this is R2. So you request and it is allocated. And then P2 release R2, so it is free. And P3 request and it's created the plotter R3. So this is P3 and this is R3. So request, allocated, finish. So it is free. So P3, this is scenario 1. There are no cycles in the directed graph. Conclusion, deadlock can occur even if each process requests every resource if the resources are released before the next process. So the keyword is if release, if not the keywords, key sentences. If the resources are released before the next process, resources are released before the next process. So R1, P1, R1. So when it's already done, deallocate, so free. R2 is serving P2. After it finish, so it is free. R3 serving P3 till finish, so it's free. So this is the perfect. This is a perfect situation. No deadlocks. Resources are released before the next process request them. Okay, it is released. It is free because it is released before any other jobs want to request that resources. Scenario 2. So P1 request allocated R1, P2 request allocated R2, P3 request and allocated R3. At the same time, P1 request R2, P2 request R3, and P3 request R1. I know this is the deadlock situation. So you have here how you have here, this is the circle. So R1, this is the previous this is scenario 1 to 3. R1 serving P1 R2, serving P2 RT, serving P3. And suddenly P1, okay, I need to access R2, block. P2 needs to access RT, block. And P3 need to access R1, block. You can see this is kind of a cycle. This is kind of a cycle, even though it's not a perfect cycle, but this is a cycle. So this is a loop. And this is a deadlock. Again, this is a sticky situation. So because deadlock, because every process is waiting for a resource held by another process, but none will be released without operator intervention, control alternate, delete, restart, or whatever, enters certain processes. So scenario 3, you have scenario 1 and 2. So P1 request and allocated R1. P1 request and is allocated R2. P2 request R1. P3 request and is allocated R3. So this, okay, it's better because this is like more action needed. So you have here, we have to see, P1 request and is allocated R1. So P1 request, so R1 currently serving P1. And P1 requests and is allocated R2, meaning that resource 1 and resource 2 is held by P1, serving P1. P2 requests R1, so P2 requests R1, so now because R1 is serving P1, so this is block. Sorry for that. P3 requests and is allocated R3. So now R3 is serving P3. Where are we now? 4, now 5. P1 release R1, which is allocated to P2. So R1, okay, P1 already finished the process. So he doesn't need the R1 anymore, so it's free. So now R2, so now R1 is serving R2. Before this is a block when this one already free. So R1 is serving P2. P3 request R2. P1 release, P3 request R2. We have a P3 request R2. Where is it? P3 request R2. It's supposed to be, okay, this is a red. P3 request R2. Okay, but it's a block. It is blocked because R2 now is serving P1. Okay, P1 which is P3 request R2. So now this is a P3 request R2. Not sure why it doesn't have an arrow here. P1 release R2, which is allocated to P3. So okay, after okay, now P1 already finished using finish his processes, so he doesn't need R2 anymore. So he released this. So now P3 instead of block, so now it is allocated. P3 now being allocated R2 resources. R2 is serving the P3. So the graph can be expanded to include several resources of the same type that can be allocated individually or in groups to the same process. Okay, so you can classify, or you can break, you can put several resources into the same type. Device of the same types, I mean, you have a printer, what else, scanner. You know, usually it's 3-in-1 now, but let's say it's 10 years ago, you have a printer, single device, scanner, single device, copier, single device. So you can put this, you can put all these devices into one entity. Device of the same type are classified into one entity. The arrows show the links between a single resource and the process using it. Single resource and the process using it. So A is stable, okay? A is stable, but when all three processes request more than one resources, so this one A is stable. But when all three processes request one more resource without using the one they are using, a deadlock occurs, okay? let's say this one is on the P1, this one is R1, and this one is R2, and this one is R3. Okay. At the same time, P2 need to access R1, P1 need to access R2, P2 needs to access R3, and P3 might need R1. So no one really, no one are releasing their resources. Okay, no one released their resources yet. So this is the deadlock situation. This is a stable situation, stable condition. Sorry, stable condition. This is a deadlock condition. Okay. Requests and releases are unpredictable, and that makes it difficult to design foolproof preventive policy. So this is a dynamic, it's interactive. Okay, it is really unpredictable. So you cannot have a system, or you cannot have a perfect design. Okay, if you do it like more locking, more this and that, you will increase the deadlock. But if you make it too relaxed, it will suffer, data integrity will suffer. So you must have a trade-off. Okay, must balance, everything must be in balance. So that's why they don't have a foolproof preventive policy. Okay, foolproof preventive policy. Maybe some other conditions, maybe some other algorithm is okay for this kind of situation, but it's not okay for different situation. So there's no one size fits all. So no one size fits all. 3 strategies to deal with the deadlocks: prevention. Okay, this, as the name suggests, avoidance and detection. Prevent one of 4 conditions from occurring. Avoid the deadlock if it becomes probable. Detection, detect the deadlock when it occurs and recover from it gracefully. So the OS must eliminate one of the 4 necessary conditions to prevent deadlock: the mutual exclusion, resource holding, okay, mutual exclusion, resource holding, no preemptive, and circular. Okay, these 4 conditions. Eliminate these 4 conditions to prevent deadlock, which is, it's not easy, it's complicated. Mutual exclusion is necessary because certain resources must be allocated to one user. Remember the example I give earlier, when you have a 2 process X, read X, write X equal to X plus 10, and this is process 1, this is process 2, read X equal to X plus 10. So this X is shared variable. So maybe you want to mutual exclusion. You want to, okay, do the process 1 first, lock process 2 from accessing X. So P1 will read X. So X equal X plus 10. So now it will execute write X plus 10. So X is 20. Move to the process 2. So P2 will read X equal to 20, X plus 10, so 20 plus 10, 30. So this is the correct. So this is mutual exclusion. You cannot do so many mutual exclusion, or you cannot do less mutual exclusion. Some of it is very important, okay, to do mutual exclusion. But if too much mutual exclusion, your system will become very slow, and it's not really effective solution. Must be balanced. Okay. Resource holding can be avoided by forcing each job to request every resource it will need to run to completion when it. Okay, you cannot hold this resource. I mean, okay, you cannot hold this resource even though it's idle. You cannot just hold this for these jobs to come in. Okay. You must force each job to request on demand, okay? When you want to use it, you demand the resource. Not that it's specifically save it for you or reserve for you. You have to request it on demand. All right. And then no preemption could be bypassed by allowing the OS to deallocate resources from jobs. So you can have no preemption. So you have if you're using the OS, so OS has the power to deallocate resources from jobs because maybe some of the jobs are coming in and it is more priority, more important than your jobs here. And circular weight can be bypassed if the OS prevents the formation of a circle. Solution is based on a numbering system for resources. Okay. Solution is based on numbering system for resources. A printer one, this number 2 and tape number 3 and plotter number 4. Let's say if a job needs a printer and a plotter, it requests for printer first. Okay, based on the priority. Okay, let's say printer, you need a printer and a plotter. So job, so it will request a printer first. It will request a printer first and then maybe a plotter. Let's say it needs a printer and plotter. So based on the priority, printer first and the plotter second. Even if not needs to use the plotter first followed by a printer, it still has to request to the printer first and use it later. All right. The job has to anticipate the order in which it will request for resources. So even if the jobs, let's say I need a plotter first followed by a printer, but it still need to request a printer first, then a plotter. This is to avoid a circle. A job has to anticipate the order. It has to anticipate the order in which it will request for resources. So jobs must request for resources in ascending order. In order is easy. I mean, in a nutshell, is in order. You have to follow the chain line of command. Printer 1, this 2, tape 3, plotter 4. You cannot override plotter number 1, printer number 2. No. If you already like decide the priority, you have to follow the order. So the OS also can avoid deadlock if it is known in advance the sequence of requests with each active process. It can avoid deadlock if it knows in advance the sequence. So this is the best if you know in advance, but not all systems are like that. So one of it is the banker's algorithm proposed by Dijkstra, regulates resource allocation to avoid deadlocks. So this Dijkstra is the person that inventing the shortest path, which is now used. I mean, it's a basic for all these Google Maps or Waze. Dijkstra, very brilliant mathematicians or physicists. Because last time there are no like because this is in 1950, 1960. There are no like science computer course. It's always either mathematics or physics. So he's a brilliant physicist and also a brilliant mathematician. So he created a banker's algorithm to regulate resource allocation to solve this problem. So the algorithm is based on a bank with a fixed amount of capital. Okay. Fixed amount of capital that operates under the following principle. Maybe the bank has 10,000. Bank only has 10,000. Of course, it's a very poor bank, but this is just an example. Banks have billions, billions, whatever. But let's say for a small example, you get 10,000. No customer will be granted a loan exceeding the bank's total capital. Huh? Yes? Any questions? Noise. Mister, I cannot it's making that sound. Okay, all of you. Okay. All right. Okay, thanks. Okay. Right, we will. No one. Okay, you have a 10,000 ringgit. No customer will be granted a loan as the bank's total. If any customer wants to do a personal loans, ask for 20,000, so straight away the bank will reject it. Okay, it's a common sense to do. It's a logical things to do. All customer will be given a maximum credit limit when opening an account. Okay, you have a 2,000, but you can use your credit limit until 3 to 4,000. This is normal for business account. No customer will be allowed to borrow over the limit. If you are if your maximum credit is 5,000, it will be 5,000. You cannot allow to borrow over the limit. The sum of all loans won't exceed the bank's total capital. Multiple users wants to borrow the money, so it cannot exceed the shilling. We call it a shilling of 10,000. So this is the case number one, case one. So we have a loan amount. Okay, C1 customer loan amount. So C1 doesn't need a loan, has his savings. So maximum credit is 4,000. So remaining credit is 4,000. So C2 has a loan amount. He wants to make a loan, 2,000 ringgits. Maximum credit that bank gave him, give to him is 5,000. So 5 minus 2, 3,000. You have remaining credit. And C3 is 4,000 loan amount, maximum credit 8,000. Of course, if you loan this is a conventional practice of bank. If you loan more money from the banks, they will allow you to maximum credit. Okay, if you don't use wisely, you're gonna be in trouble. I hope when you graduate, you know how to manage your financial. That is very important nowadays. Manage your financial. Okay. Don't go buy expensive stuff. Live within your means. Okay, we continue. So remaining credit is 4,000. So the loan is 2 plus 4, 6,000. The total capital fund 10,000. So bank still have 4,000 extra to play with. So 4,000 can at least the banks can at least the minimal condition. Banks can satisfy the requirement of remaining credit one of the customer. So at least like customer 1, 4,000, 3,000, 4,000. So all the remaining credit from the customer is less than the balance of the is less or same with the balance of the bank. So bank can satisfy if, let's say, remaining a user C1 wants to, I have a very important order, but I need 4,000. So bank can satisfy that requirement. So this bank is in a safe state. Okay, still have 4,000. So the bank still has enough money. So this is a safe state because the bank still has enough money to left to satisfy the maximum request of C1, C2, and C3. Not all C1, C2, and C3. At least one C1, C2, and C3. Okay. Now this case number 2. Okay, business is expanding, growing, and stuff. So C1, in order to expand his business, he needs to make a loan. Before this, no loan, using all his savings. No, business is expanding, his economy is good, whatever. So he wants to do a loan amount to 2,000. So maximum credit 4,000. So he has remaining credits of 2,000. So loan amount C2 wants to add another 1,000. Okay. I want to expand. I want to buy this machine whatsoever. It cost me 1,000. Loan from the bank. And then the remaining credit is 2,000. And C3 also, the loan amount stays here. Okay, that's why I loan more at the initial phase or at the beginning, so that I don't have to loan from the bank after that. Okay, so C3 remains static. So total loan now is 9,000 by adding 2,000 and 1,000 here, so 9,000. Total capital fund is 10,000. So you have bank only have 1,000 ringgits to play with. So 1,000 ringgit cannot even satisfy any of the remaining credit. Okay. So this bank is an unsafe state because only 1,000 is left and the banks cannot satisfy anyone maximum request. Let's say if the bank lends 1,000 to anyone, it will be a deadlock. Let's say, okay, C1 need another 1,000. So 1,000 if loan to the C1. Okay. So now at the moment, okay, C1 wants to loan, C1 want to loan 1,000. Okay. Instead of 2,000 become 3,000. Now the loan, the bank only have 0, which is a very bad management of the bank. The bank should not have 0 in his account. Okay, but this is just an example to show you. It will be a deadlock. Okay, the bank cannot make a loan. So the bank cannot cannot give loan to anyone. An unsafe state does not necessarily lead to deadlock. So this 1,000 is not a deadlock yet. Okay, 1,000. So bank has zero. Bank has 0 fund now at his current account. But this is not a deadlock yet. But it is a potential, sure to be deadlock. Okay, sure to be deadlock in the future or next few days.
Doctor,
Yes.
how do we decide if it's in an unsafe state?
So this is the situation with the unsafe state. Okay, you have 1,000 here, and the remaining credit here, based on the jigsaw algorithm, it cannot satisfy the remaining credit of any of the users. So this is unsafe state. But this is not a deadlock yet. This is unsafe state, which is a logical things. Okay, you have 1,000. Bank only have 1,000. It cannot serve. Let's say C1. Okay, I need to use the whole of my remaining credit. The bank cannot satisfy that because bank only have 1,000. This situation, bank have 4,000. Okay, not all the users, but at least single users. So bank can, let's say C1 have, okay, I need to use my remaining credit. I want to expand my business or something else. He want to buy in bulk, so he need 4,000. So he can satisfy C1. He can also satisfy, bank can also satisfy C2 and C3. Not all of it in one time, but at least one user. So 4,000. This is a safe state. Okay, 4,000 equal or more than the remaining credit. Look at this situation, 1,000. Let's say C1 I want to use the all remaining credit. No, I only have 1,000. Bank said, you cannot have your remaining credit. Maybe next month or next 2 months. Okay, when I have my payment back from other borrowers, something like that. So this is unsafe state, and unsafe state is not a deadlock yet. Okay, but it's a potential, sure to be a deadlock after this. Okay, sure potential. Yeah.
So if, like, say, in this scenario, if the total capital fund left is like 2,000, is it still considered safe or is it unsafe?
If it is a 2,000, it can satisfy at least a single user, C1 and C2. So it still is a safe state, but safe state is on the borderline. You know what I mean? On the borderline state, something like that. Okay. Just
thank you.
Okay. At least a single user, the bank can. But this one not. The bank cannot satisfy any users the remaining credit. So this unsafe state is not a deadlock yet, but it's sure to be deadlock. It's a potential to be a deadlock. Okay. The bank should not operate like this. So as long as the bank's capital is less than the maximum amount available for individual loan, it cannot guarantee that it will be able to fill every loan request, right? So this banker's algorithm. a famous algorithm for a resource, we call that how to manage your resources, banker's algorithm. Another thing is to note is the customers are not required to request for a maximum loan, but the bank doesn't know the exact amount that will eventually be requested. Okay, customer doesn't really need remaining credit 2,000, maybe enough for this, but bank doesn't really actually knows what customer wants next or in the future, or what eventually customer will request. It just have 1,000. Okay, the memory left is maybe the CPU usage only left 10%. Okay, but the CPU doesn't know how many it cannot know beforehand how many resources that the jobs need. Okay, the jobs can request maybe 20% of the CPU, so CPU cannot satisfy that because CPU only left 10%, and if job requests 20% of the CPU, sorry, I cannot entertain you because I have 10% left, so you have to wait. So this banks, what you call it? What? I forgot already. Banker's algorithm. Sorry, banker's algorithm. You call it. So you can replace this loan amount to the device allocated. Okay. Loan amount you can replace with the device allocated. Maximum credit you can maximum required, and then remaining credit remaining needs. So you can. So in a safe state, okay, at least one job can finish. Safe state, at least one job can finish. All right. So total number of devices allocated is 6. This same with the case 1 of banker's algorithm. Number of devices in the system 10. So safe state 6. 4 are still available. Safe state. So 4 can request job number 1, job number 2, or job number 3, provided they don't request it at the same time. So this same with the case 2 of banker's algorithm. So only one device cannot satisfy job number 1, job number 2, or job number 4 because they only have one device left. Okay. This is an unsafe state. Again, unsafe state is not a deadlock situation, but it's a potential OS. Intelligent OS must realize this. Okay, we are now into the unsafe state. We must do something. Okay. All right. Unsafe state is not a deadlock yet, but it's a potential to be a deadlock. So the OS must be sure never to satisfy requests that move it from a safe state to unsafe state. So the good OS must know this, able to sense this. Okay, must be sure never to satisfy requests that move it from safe state to unsafe state. When a request is received, the OS must identify the job with the smallest number of remaining resources. So identify the job with the smallest number of remaining resources and make sure that the number of available resources is at least equal to the number needed for this job to run completion. Okay, meaning that this one, 4 is equal to the remaining jobs. He wants to, the device want to satisfy the job requirements. Make sure that the number of available resources is at least equal, keyword equal, to the number needed for this job to run to completion. Again, this banker's algorithm is created like 1950. So it's like around 60 years ago. Of course, at that time it was brilliant, but it's also from this we can learn it's not a practical. Okay, as a job enters the system, it must predict the maximum number of resources. As a job enters the system, you might never know. Maybe your files may be added like a lot. Maybe your program, I mean, if you coding, when you add the data structure, or you want to do a simulation, you don't know, maybe your simulation in the future, when you add some command, when you add some lines to do jobs, maybe maybe it become bigger and bigger. So you can never know what is the maximum number of resources you need. Not practical for interactive systems. The number of total resources must remain constant. If a device breaks, if a device breaks, let's say you have two SSD drive, and then one SSD drive breaks, so the algo won't work on this type. It doesn't have a foolproof or fault tolerance. We call that a fault tolerance. It doesn't have a fault tolerance to deal with this if device breaks. The number of jobs must remain fixed. Not possible in the interactive. This interactive system is on demand. Can add it, you can add it, or you can deallocate or something. It cannot remain fixed. Of course, it is a certain job situation you must remain at a fixed. Fixed not fixed partition, fixed allocation. But it's not a good way to manage jobs or OS. Or OS. So the overhead cost of running avoidance algo can be quite high. Okay, of course you can just let it run, but if you want to avoid a deadlock or starvation, it can be this overhead. Okay, this is your normal code. If you do a programming normal coding, maybe you have 20 lines. But if you want to add the avoidance algorithm, maybe it becomes like 50 lines or something, more than 20 lines. So this is an overhead. This overhead will increase processing load, will increase heat, whatever your OS. Your OS has to work more. It has to be in for each. There are many active jobs and many devices, because it has to be invoked for each request. Resources are not well utilized because the algo assumes the worst case, hence keeps vital resources unavailable to avoid unsafe states. So, if you assume the OS always assume the worst case, it's not a good system, okay? Because it will keep the vital resources, the most priority one, unavailable. No, you cannot use this unless it's very important, because the OS want to avoid the unsafe states. Scheduling suffers due to poor utilizations. Okay, if you just keep some resources unavailable, it's wasted. So scheduling suffers due to poor utilization, and jobs are kept waiting for resource allocation. Keep waiting and waiting. May lead to indefinite postponement of a more complex job requiring many resources. So it can lead to indefinite postponement. Postpone. Waiting. Job cannot run. Of a more complex job requiring many resources. Of course, you can just restart, Control Alternate Delete, and task, something like that. But it's not. It is effective, but is it a good way to do that? No, it's not really a good way, but it works every time. So detection. Deadlock can be detected by building directed resource graph. Again, resource graph. You mean a resource graph, you build a node, and then you put a line, whether it's you have an arrow here, it's a directional, or just this graph. If no arrow, meaning that it's a bidirectional. This just a graph theory. The way you visualize a node or whatsoever, it can be engineering, it can be a protein based. If you learn chemistry, in a protein or organic chemistry, or in like Waze or Google Map, it's like node is a source to destination, something like that. It's a graph theory, just a way for you to visualize a situation. And looking for cycles. If it's a cycles, it is not good. Okay, it's a loop. If you detect a cycle, a loop, going in loop, meaning that you are in deadlocks. The detection algo can be executed when appropriate, every hour, once a day, when there is noticeable throughput degradation. Okay, your OS, good OS, we have data analytics. Okay, day by day. Okay, when you run the simulation, when you run a video rendering will take a lot of resources. Okay, your system will become slow. Maybe okay, when you do like me, like video rendering, I can check. For your classes, when you do video rendering, try to break it out into smaller. Takes a lot. You need a really powerful PC with a GPU. You want to buy a new PC, buy with a GPU and RAM at least 16 gigabyte. Okay, the detection algo reduce a directed graph. So if you do algo, you reduce a directed graph, meaning that more resource will become free. Or you detect this, so you do something, so you can free. You can free the allocation. You can deallocate. You can free the resources quickly or in the most effective manners. So steps to reduce graph: find a process that is currently using a resource and not waiting for one. Find a project currently using a resource and not waiting for one. Remove the process from the graph by disconnecting the link tying the resource to the process. Disconnecting the link tying the resource to the process. The resource is returned to the available list. Of course, you cannot just simply disconnect the link tying. If you do a video rendering, if you disconnect that or you stop that, you have to do it all over again. Only on the jobs that can be resumed later, where you can, okay, this the whole process, maybe this jobs coming in, so you can stop here, you mark here, okay, this is where the job stops. So you do other process as well, most priority, then you come back here, you continue. So if this this jobs, it's not really priority, but it's use a lot of resources, you can just stop, pause. You mark terrible, mark. Okay, you mark where you stop the jobs current. Then you go do something else. Then you come back, you continue where it stops. In the point that where you stop, you continue from there. Cannot just simply disconnecting the link. Okay. Find a process that is waiting for resource class that are not fully allocated. So process that is waiting for resource classes that are not fully allocated. This process does not contribute to the deadlock since it will eventually get the resource it's waiting for, finishes and return the resource to the available list. Okay, so logical things to do. Not fully allocated, it's like the smallest job or something, that low hanging fruit. Okay, you can give this job because it's not affecting anyone. You can just give these jobs go first, execute first, finish, clear the resources. Go back to step 1 and continue with steps 1 and 2 until all lines containing resources to process have been removed. So the goal is like this nodes. So you have here, then maybe you have here. The goal is to remove the all lines connecting, to release the resources, to freeing the resources. Okay, in A, okay, this go to A. Okay. This, okay, circle is what? Circle is process. Circle is process. Rectangle or square is resources. Okay, you have P and R. P process, R resources. So now P1, P1, R1, resources 1 is serving a P1. Resources 2 serving a P2, resources 3 serving a P3, okay? And at the same time, P1 wants to access R2, but now R2 is serving P2, so block. P2 tried to access R3, but now R3 currently serving P3, so this is also block. All right. So now, okay, B. Okay, we have a situation, okay, B. Now, now, okay, at the moment, after sometimes R3, P3 already finished using, finish its jobs. So it doesn't need the R3 anymore. So, doesn't need the R3 anymore. So, it will release this one, and R3 will be allocated to P2. Now P2, we call that P2. P2 already finished using R2 and R3. Okay, P2 already finished using R2 and R3. Since P1 request for R2, so R2 now will be allocated to P1. Before this, it is blocked. So now R2 is what? Serving P1 with R1. And D is after P1 finish the jobs, he doesn't. Okay, I already finished the jobs. Terminated it, and it will free the resources of R1 and R2, and this is the everyone happy. Okay, all are free, everyone happy. Can do a perfect square, sorry. So this D is when the resource already all being freed. If there are any lines left, this indicates that the request of the process cannot be satisfied and that a deadlock exists. If there are any lines left, this indicates that the request of the process cannot be satisfied and a deadlock exists. The flowing graph shows a deadlock situation. So you have here, okay, P1, this I think this is self-explainable, same like P2 tried to access R1 but now it's serving P1, so okay, P2 tried to access R3 but now it's calling P3, and P1 tried to access R2 but now R2 serving P2. Okay, now P3 already been released, and now R3 is allocated to P2. Now it's serving P2. But still R1, P1 doesn't release R1 yet because still has to finish its jobs. And R2 also still using is still used by P2, and P2 doesn't release the line yet, doesn't release the resources R2 yet. So this is blocked, still blocked. And this, when this happens, you have a loop here. You have a loop, or something like that. Loop. It doesn't matter how you draw it. It's a loop. So when it's a loop, it's a deadlock. You want to avoid this. Once a deadlock is detected, it must be untangled and the system return to normal as soon as possible. Recovery algorithms require at least one victim and expendable. So you have in your team members, those with the weakest link, those with become a victims. Okay, like you have a company and you have a company with 5 workers, and then maybe business not growing so well. You have to set one people, so you have to find a victim. We call that it is expendable, which is very, but sometimes you have to do that. No, in certain circumstances or difficult situation, you have to do that. You must be a bad guy. Removing the victim, but of course you cannot simply removing. You have to select one of the, the expendable. Those are expendable. Those are the weakest link. Removing the victim from the deadlock will free the system. Okay. The job that becomes a victim has to be restarted from the beginning or from a convenient midpoint. Okay. The jobs, maybe if like you do certain, like I say, video rendering, you cannot stop. You have to finish it. If you stop it, you have to restart. You have to start all over again. I'm not sure if any software that can do that. I'm not very good in the multimedia, but I think you cannot do that. And then maybe some of like downloading a file from torrent or download, you can stop at a certain point. Okay, stop at 52%. Maybe you can continue later. Okay, something like that. We just have a couple of slides to finish. Just bear with me. As simplest and most drastic approach to terminate all active jobs and restart them. Method 2, terminate only jobs involved in a deadlock and task the user to resubmit them. Okay, you can do a control delete and task certain jobs if your computer becomes slow. Method 3, to identify jobs involved in a deadlock and terminate them one at a time. And then checking to see if the deadlock is eliminated after each removal. Okay. So first, simplest, I'm going to find a victim. Simple and most realistic is terminate all active jobs and restart them. Close, restart the PC, push a shutdown button, something like that. Simplest. Method 2, terminate only jobs involved with deadlock and ask the users to resubmit them. When you see, sometimes you see a pop-up, okay, it's unresponsive. You control the delete, you delete that, so you remove the deadlock. Method 3, identify jobs involved with deadlock. Maybe I think this program taking along or taking more resources, so you terminate them. So method 4 can only be used of the job. E of the jobs keeps a record, snapshot of its progress, so it can be interrupted and continue without restarting from the beginning. This is the best. The snapshot is like the landing in the staircase. Instead of forcing a ascender-descender to return to the bottom of the staircase, he only retreats to the nearest landing and wait for others to pass. Okay, maybe a certain stair you have, you only retreat to the nearest landing, okay? Instead of going down all the way down, go to the nearest landing point and wait for others to pass. Become a man, become a good man, and then okay, sorry. Method 5 selects a non-deadlock job, preempts and resources you're holding, and allocates them to deadlock process so it can resume execution, thus breaking the deadlock. Okay. Non-deadlock job preempts the resource is holding and allocate them to the deadlock process so it can resume, thus breaking the deadlock. So method 6 stops new jobs from entering. Okay. Reason to allow non-deadlock jobs to get resources, they need to run a completion. So factors to consider when selecting a victim with at least negative effect on the system. Priority of job. So of course, the high priority jobs are usually untouched. CPU time used by a job. Jobs close to completion are left alone. Yeah, I need just a little more, just a little bit time, like this one, just to finish the lecture slide. Okay, the number of other jobs that would be affected if these jobs were selected as the victim. Okay, number that would be so like if you really say HR is a company, you really set an important person, a system engineer or programmer, without having without replacing equivalence to, I mean, without replacing sometime someone that is really high skilled to do their jobs. Your system will be I mean, it will, no, your all other departments, the company will become very messy and uncontrollable. Okay, so choose your victim wisely. Choose your victim wisely. Okay, starvation, the last one, is the result of conservative allocation of resources where a single job is prevented from execution. Okay, this starvation is worse than a deadlock because you keep waiting for resource that never becomes available. Okay, the dining philosophers of again from Dijkstra, this is a Dutch guy, okay, very brilliant mathematician and physicist. So he introduced a dining philosophers. So the philosophers sit around a table, each deep in the thought. All these philosophers. In the center is a bowl of spaghetti. There are forks between each philosophers, okay? So there are forks between each philosophers. The philosopher must use 2 forks on either side. So in order for the philosophers to eat, must use on either side, because you have 5 philosophers. The ideal number of forks is 10. But now you only have 1, 2, 3, 4, 5. And you must use both forks to eat the spaghetti. By the way, it's not look very, I mean, yeah, talking about foods, because this is the last, I think, for Muslim, this is the last day for you to eat before tomorrow you have to start fasting. Okay. Just bear with me before you want to have your lunch. Just this final slide. So the philosopher must use two forks on either side. So a philosopher can only eat or think at a given time, but cannot do both. So philosopher can only philosopher need to think or eat, but you cannot do both. Okay. If you don't eat, you think. If you eat, you cannot do anything. You cannot think anything. You just eat. Don't think. All right. A philosopher can only eat, think, will eat or think at a given time, but not cannot do both. Okay. First, P1. Okay. First, P1 now wants to eat, so it will take F1 and F5. Okay. P1 is the first to start eating using the F1 and F5, and then P3 does likewise. P3 also eat, so it using F2 and F3. Okay, so now P4, P5, and P2 cannot eat. Although they are hungry, they cannot eat. Same like you, although you are for lunch now, you cannot finish yet. Here's a little bit more. P2 decides to begin the meal. Okay, P2 decides to begin, but is unable to start because no forks are available. So P2, P4, and P5. P2 is hungry. I'm so hungry, but I cannot use the forks because now is F1 is P2 can only use F1 and F2, but F1 currently using by P1 and F2 currently using by P3. Okay, okay. Now, okay, like P3 finish eating. Okay, release the F2 and F3. Okay, without washing the fork. Okay, now P2 realize F2 is free, but not F1. Still, he cannot eat that because he has to use both, one left and right. So P4 and P5 are still thinking. Okay, P4 and P5, maybe they have lunch earlier, so they're still thinking. P1 hasn't finished eating yet. P1 is eating a lot of it. Okay, P1 is eating and not thinking of others. P3 decided to eat again. Okay, P3. Okay, I finished eating, but now I want to eat again. Still not enough. I think I eat too little. I want to eat again. So P3 use F2 and F3. P2 is like really hungry. His tummy already make a sound or something, but he still cannot eat the pasta. Okay. All right. And then P1 finish. Okay, I think I think I am full. So I release F1. But P2 still cannot eat because F2 is used by P3. So it can become so this scenario could continue forever. Okay, P2 cannot eat. P2 can call it starvation. P2 can die of starvation, or of course he went out and take out or something. Okay, result required is never released. So in computer, final slide. In the computer environment, the resources are like forks. And the competing processes are like dining philosophers. Competing processes, jobs. And this one is resources. Process or jobs, process. If the resource manager does not watch starving processes and jobs and plan for their completion, they could remain in the system forever. So manager does not watch for starving processes. This process have it for very long times and does not plan anything for them, it could remain in the queue forever. Once the system is detected, the system can block new jobs until the jobs have been satisfied. Okay, so thank you very much. That's it for today. For Muslims, happy fasting, everyone. Is there any questions? Okay, Okay, so today I will actually, sorry, record. Okay. Uh, okay, that's it for today. For Muslim, this is your final lunch before you start fasting, and for all, for all, good luck and everything. Okay, thank you very much.
Thank you, Doctor.
You're welcome.
Thank you, doctor.
Thank you, doctor. Thank you, doctor.
Right. Okay. Sure.
Thank you, Doctor. See.
All right. I think there's a recorded and if you want to see the recording first before I upload, you can see in the team. Okay. Have a nice lunch. Don't go into the T-Star Freedom Starvation. Okay.
Doctor,
Okay.
Doctor, sorry.
Yes.
Can I ask for mid-sem exam? Will cover until which chapter?
I will. Okay. I will discuss this one, Fazida. I will inform in the either in Spectre or in the team. Okay.
Alright, thank you.
Basically, what you have learned. All right.